days, you'll be given a sample of silver oxide. You'll be able to figure out how many grams of silver and grams of oxygen were in that sample. And by knowing those, you'll be able to figure out how many atoms of silver and atoms of oxygen were in that sample. And so you'll be able to figure out the ratio of silver atoms to oxygen atoms. You'll figure out the formula of silver oxide. But in order to be able to convert from your grams into your atoms, you'll need to convert first into moles, which are kind of like little cute creatures, except in chemistry, it's actually just a number of something. Yeah, in chemistry, a mole of something, a mole of representative particles is 6.02 times 10 to the 23 particles. That's a lot of particles. Why such a crazy number? Why do we have this Avogadro's number, a famous number? Well, it's because it turns out a gram of something is 6.02 times 10 to the 23 atomic mass units, which are about the mass of a proton or neutron. So a mole is really just a number of something, a really big number of something, but it's kind of like dozen. A dozen of something is 12 of something, and a mole of something is just 6.02 times 10 to the 23 of something. And those somethings, those representative particles, can be either atoms, like He, helium, or neon, or they can be molecules where there's multiple atoms bonded together, which are all nonmetals or metalloids, so like O2 as an example. Or we can have formula units, which for ionic compounds. Yeah, those have metals and nonmetals, ionic bonding, so we wouldn't say that they are molecules. They're formula units. So calcium chloride is an example. Okay, so let's say that you had 1.24 times 10 to the 24 methane molecules. Methane, which is in our natural gas that we heat our homes with. How many moles of methane do you have? All right, so go to your trusty mole map. We have molecules, a type of representative particle, and we want to go into moles of them. And so we need to go to the left. And so we're going to use this unit conversion factor right by the left arrow. So we start out with our certain number of molecules, and then we'll multiply by 1 mole over 6.02 times 10 to the 23 molecules. We have 1.24 times 10 to the 24 CH4 molecules, and then put molecules on the bottom, cross it out, and convert into moles. Per 1 mole, there's 6.02 times 10 to the 23 particles. But when you plug into your calculator, be careful, because there are multiple numbers in the denominator. And so a lot of people accidentally divide by 6.02, but then they multiply by 10 to the 23. But 10 to the 23 is on the bottom, so we want to divide by it. So either use parentheses around everything in the denominator, or do 1.24 times 10 to the 24 in your calculator, hit enter, then divide by 6.02, hit enter, and then divide by 10 to the 23 and hit enter. So you get 2.06 moles of methane. Now, let's say that you had a certain number of grams of methane and you wanted to figure out how many molecules of methane there were. Well, then you would need to know the molar mass of methane, the number of grams per mole. And so you can get that from the periodic table. On the periodic table, you'll see that carbon has an atomic number of 6. It has 6 protons, always. And then it says C, and then it says 12.01. So that is the average atomic mass of all of the carbon atoms on Earth. And so the weighted average atomic mass is 12.01 AMUs. That's the mass of a carbon atom on average. But if we have an entire mole of carbon atoms, then we have 12.01 grams of carbon. It's the exact same number. And that's because of the mole. It's because of our choice of 6.02 times 10 to the 23 representative particles per mole. It's because per gram there are 6.02 times 10 to the 23 AMUs. Doesn't really matter why, though. You just need to know that on the periodic table, that 12.01 right below the C is the molar mass of carbon, the exact same number as the atomic mass. So similarly, if you can find the molecular mass of methane, you can find the molar mass of methane. It'll be the same number. To get the molecular mass of CH4, then you need not just the mass of a single carbon, 1 times 12.01, but also you need to include the masses of 4 hydrogens. So 4 times 1.01 from the periodic table just below H. So all of that adds up to 16.05 AMUs. That's the molecular mass, the mass of a single molecule of methane. And so exact same number, there are 16.05 grams of methane per mole. That's the molar mass. And so if we have 0.48 grams of methane, we can convert into molecules of methane by going from grams. We'll next go into moles by going to the right, by multiplying by this unit conversion factor, 1 mole over the molar mass of methane. So we had 0.48 grams of methane, then multiply by 1 mole of methane over 16.05 grams. And then we'll convert from moles into molecules of it by going to the right, multiplying by this unit conversion factor, 6.02 times 10 to the 23 molecules of CH4 over 1 mole of CH4. Yep, that way grams of CH4 is on top and bottom, it cancels. Mole of CH4 is on top and bottom, it cancels, and we'll be left just with molecules of CH4. And then finally, sometimes you'll need to convert from liters or milliliters of a gas into these things. And so it's helpful to know that a mole of gas, if you're at standard temperature, so that's 0 degrees Celsius, the temperature at which water freezes. And if you're at standard pressure, 1 atmosphere or 101.3 kilopascals. If you're at STP, then a mole of gas occupies a beach ball volume, 22.4 liters. So you could convert from liters into moles by multiplying by 1 mole over 22.4 liters, and then you can convert into other things if you need. All right, thanks for watching, y'all.